fundamental physics that we can fundamental physics with Lisa from Saeed, who's coming to us from the University of Alberta. Saeed, I will hand it over to you, and I'll give you that annoying 2-minute notice, and then you can adjust as appropriate.
Thank you very much, Darren. Thanks everyone for being here. So I'm tasked today with presenting a few of the tests that Lisa can do about fundamental physics. Of course, there are lots of interesting and exciting tests that is going to be done by Lisa. I'm just in 15 minutes, I will have time to just present a few of them. So first of all, excuse my voice. It's a little bit worse today. So there are lots of tests that Lisa is going to be able to do about a host of phenomena, from classical gravity cosmology, from validity of the classical GR, alternative theories of gravity, different types of classical black holes and dark energy, dark cosmology, all the way to quantum gravity. Very interesting issues like the fine structure of space-time, quantum black holes, even early cosmology beyond the last scattering surface, the physics beyond that, and dark matter and astroparticle physics. So of course, there were lots of great talks yesterday and today. They had some interview or overview actually of the whole Lisa science. So I decided not to do an overview, just focus on a few of these. So for more, you can look at the paper, Lisa paper, white paper about the fundamental physics tests. I'm just gonna talk about these 4 blue topics: alternative theories of gravity, quantum structure of space-time, quantum black holes, and a little bit of dark matter. Okay, so let's start with alternative gravity and see some of the tests that Lisa can do. Of course, we all know that in classical gravity, classical general relativity actually, you can write the perturbations, you can write the equations of motion, etc., and you will find out that in transverse traceless gauge, you only have 2 polarization, which are well known as plus and cross. And this is how 3-dimensional and 2-dimensional they would look like. This is what we have observed in Ligo and Virgo. And if you proceed to quantize this using usual quantum field theory, you get this massless spin 2 field, which is basically the particle of this field is a graviton, well-known graviton. Now, if you move on to alternative theories of gravity, things start to change. First of all, you might still get plus and cross polarization, but then they might be different in some ways. There will be modifications to that. And more importantly, you get a scalar probably, and in many of these theories, a scalar and vector modes too. So the decomposition into a scalar, vector, and tensor is a kind of algebraic decomposition, and turns out that in GR, classical GR, only tensor modes pop up. But in alternative gravity theories, you have other modes, and they might be also massive. Let me give you an example. So these are a class of theories are called F of R theories of gravity. So instead of having just R here, which is Einstein-Hilbert action, usual classical general relativity, you have a function of this Ricci scalar. And this should admit some symmetries, but apart from that, you're free to choose whatever you put here. And if you compute the gravitational or perturbation or gravitational wave corresponding to that, you will see that you have the usual suspects, the plus and cross polarization, but you have additional scalar massive mode here. And this, in addition to being an additional mode, the velocity of or speed of the propagation of this mode is actually different from the speed of the propagation of the other modes, which is the speed of light. Here is different. And so with this, one can, or Lisa actually can limit or refute, or well, prove if you want, some of the theories of alternative gravity. In fact, you can, on a FLRW background, cosmological background, in transverse traceless gauge and in Fourier space, you can write the equations of motion of these perturbations for a general case. And if you forget about this h, which is the Hubble rate, and this is the speed of the propagation, I will talk that in a little bit, but if you put v and gamma equal to 0, you basically get the usual wave equation for the gravitational waves in classical GR. However, in this case, we can parameterize this for basically more general theories. H is the Hubble rate, basically A dot over A. This gamma here represents amplitude damping. If you have gravitational waves where amplitudes are different from the classical GR, and if your propagation speed is different from the speed of light, this parameter would be different. And finally, the function D here represents modification to the dispersion relation, which is basically omega squared equals k squared, for example, for the massless particles. So I can't see the chat, but I think there are some things. Anyway, so Lisa can actually do experiments on propagation of propagating gravitational waves and put a bound on these parameters, and by that it can limit alternative theories of gravity and refute most of them. That is actually what we want from science. We mostly want theories to be refuted and limited. An example of how Lisa can do this actually comes from what we have already, or what people have already been doing using Ligo and Virgo. In 2017, there was a neutron star in spiral. The team from Ligo and Virgo observed it. This is the picture below here, and almost immediately after that, 1.75 seconds later, a gamma ray burst was observed by Fermi Observatory, and from the same part of the sky. And assuming that they're coming from the same source, and using the luminosity distance of the gravitational wave signal, and also this time delay that I presented here, they found that the speed of the gravitational waves should be limited or constrained to 1 part in 10 to the power 15. So we already have a strong bound from Ligo Virgo, and this refutes many of the alternative theories of gravity. But Lisa can certainly significantly improve this bound and give us better results. The next topic I'm actually briefly will be talking about is dark matter. It's very important for people in the dark matter community to find or shed light on the particle nature of the dark matter. And one of the methods, which is a promising method, is called the dark matter spike. A dark matter spike basically assumes that around black holes you have higher density of dark matter than farther from black holes, and that's called a spike or dark matter spike. Now, if you put a binary system in this spike, basically another compact object around the central black hole, the dynamics of this system will change due to the presence of dark matter, and consequently the pattern of the gravitational waves will be modified. And this is a schematic version here. You see the no dark matter and dark matter cases. There's a phase shift here. This helps us actually in finding the dark matter density profile. And finding dark matter density profiles leads us to information about the particle nature of dark matter. I'm not going to talk or go into details about this. But you can go to the first lightning session talk by Diego Montalvo. He will present some sensitivity plots and etc. about a model that was developed. So another interesting possibility, which is probably first in human history, is possibility of checking the quantum structure of space-time, whether there's such a thing as quantum structure of space-time. So space-time, although it's very familiar, probably is the most mysterious thing we have in physics. Part of it is because it's very familiar. Most of the people in quantum gravity community believe that continuous space-time might be an illusion, and there is something more fundamental under the substrate under this, what we call the continuous space-time, and that thing might be discrete or quantum. And from coarse graining of that substrate, you get the smooth space-time. This is something like thermodynamics and statistical mechanics. You have a bunch of atoms, you coarse grain that, and you get some sort of a smooth gas. It looks smooth, but it's actually not. So this substrate might actually give us the solution to the problem of singularities in gravity. Anyway, so the question is that what is the final structure of space-time? Is it fundamentally discrete or not? And surprisingly, Lisa can help us in shedding light on this. To mention how, yeah, we know that quantum gravity or most of the theories of quantum gravity and quantum space-time, they actually, because they quantize the metric, at some level they give us effective metric or effective perturbations or both. And these effective structures, they definitely modify the production and propagation of gravitational waves. And this actually leads to different signals. As an example, we have this model based on or inspired by loop quantum gravity, for which if you compute the strains, the perturbations, you will get something like this. And if you look at this, you have the usual cosine function with this amplitude here, but you have higher harmonics, you have amplitude modification or damping here, this function f, and also you have a modification to the dispersion relation or Lorentz invariance violation and propagation speed modification. So the propagation of the gravitational wave in this model will also be modified. This mu here is a parameter, a quantum gravity parameter, that basically sets the minimum scale of the theory or minimum scale of quantum gravity. So you see that the larger this mu, the larger the effects that you will see in this model. So we can test this model by putting two equal mass inspiring black holes at z equal to 0.3 and see if actually these effects, the modification to the pattern of the gravitational waves, can be seen by LISA. And surprisingly, this is rather a semi-conservative computation, and that shows us that for some of the binary black hole binaries, the difference between the classical and quantum versions, the classical and modified versions, is, I mean, LISA may be able to observe these, which is very interesting and very important. This has not been done before, and the possibility was not before. So that's about the structure of space-time. The final part of my talk is about spectroscopy of quantum black holes. So this is again something about quantum gravity, and this has not been done before LISA, and LISA will reach the sensitivity to actually do experiments on this. Let me give you a sketch of how it works. So a long time ago, 1970, I think 4 or 5, Bekenstein, based on the observation that the area of black holes are adiabatic invariants of general relativity, concluded that the horizon area should be quantized, the area of the black hole. On the other hand, the quantization of the angular momentum of the black hole also leads to the mass spectrum or energy spectrum of a black hole to be discrete. Now, this is very crucial. When the energy spectrum of something or black hole is discrete, this reminds us of the atoms. Remember that atoms can only emit or absorb energy in certain, discrete frequencies, quantum packets, and the same should happen to black holes if their mass or energy spectrum is discrete. So they can only absorb gravitational waves in certain packets, in certain frequencies. And that allows us, to test the discreteness and area and the mass spectrum of the black hole using gravitational waves by LISA. And the big question is that, okay, so these discretizations are of the Planck scale. So how do you expect this to show up in low frequency gravitational waves? And the key here is the mass of the black hole. So there's something called the first law of black hole mechanics. And based on that, if you do the computations, you will see that if the mass or the energy of the and the area of the black hole is discrete, we'll find that the omega, or the frequency of the absorption of these of waves, basically, or energy, goes as 1 over the mass of the black hole. And surprisingly,
Saeed, this is your
yes,
your 2-minute heads up.
Okay, thank you. Yes, so if you have a black hole of mass of n times the mass of the sun, it turns out that if you can compute the frequencies, and the frequency of the gravitational wave that can be absorbed, these frequencies of the small packets, is basically 1 over pi n. So for a black hole of a few thousand mass of the sun or larger, so these frequencies are within the observation of the LISA observation capabilities. the idea is that basically, let me go very fast. During the ring down, some of the radiation of the gravitational waves of the system, of the binary, if you want, goes down to the black holes themselves, but that might not be absorbed because of the phenomenon I mentioned, if the frequency is a certain value, and then it will be radiated out again. It goes back to the photon ring, and from the photon ring, it will again be scattered back inside and outside, and this goes on, and you get a something that is called the echo of gravitational waves of black holes. And you see here these red bands correspond to the angular momenta that are, the highest that give you the highest probability of these echoes. And these are the frequencies. The red one is the frequency to the most probable quasi-normal mode. So anyway, these echoes would be, LISA would have the possibility of observing these echoes and give us information about the discreteness of black hole mass and area. So in summary, I would say that LISA gives us a great opportunity to test fundamental physics that was not possible before, and these are quantum gravity grade tests. And really, I myself, I'm really excited to see these tests done. These tests have a range of, modified gravity, astroparticle physics, all the way to quantum spacetime and quantum black holes. And having said that, I mean, you're all invited to join this journey if you like theory, data analysis, software, hardware, experiment, whatever you like. Because all of them are available in this LISA experiment. Thank you very much.
Awesome. Thank you so much, Saeed. Let me pull up my list here. So fantastic. I see some thank yous. Eric, please go for it.
Hey, Saeed, thanks for the talk. Good to see you again. I was just wondering, with the black hole spectroscopy, I guess what were the limitations for Ligo and Virgo in that? Like, is there any availability for tests on those fronts, or is there just sensitivity issues or frequency issues?
Yeah, there's for Ligo and LISA, they don't have the sensitivity to observe these or test these effects. That's why we're all looking for LISA to do these.
Gotcha. Okay, thank you.
Sure.
Thanks. Do we have any more questions? I think I see, oh, Eric, maybe, do you have another question? Is your hand's just still up?
Oh, sorry.
No problem. Great. So Saeed, I guess I'm wondering, like, this is a little bit of a vague question, but one of the things that we can offer, I think, as a Canadian community has to do with our Compute Canada and other compute resources. How maxed out, how far are you pushing those things? I mean, what is the sort of infrastructure that you all need from the theory side to really be able to undertake the tests you want to make and prepare for something like LISA?
Right. So for computational part, you're right. We really do need the capacities of Compute Canada or even more, because just to give an example, one of our computations about these quantum black holes and the effects for quantum gravity took around 6 months just to run on a huge platform of several cores and everything. So yeah, we're looking forward to all these possibilities of computational capacities if possible. Unfortunately, there are a few things with Compute Canada. For example, we cannot run Mathematica on it still, but hopefully in future that would also be resolved.
Yes, analytic theory needs Mathematica. Great, good. Okay. Do we have any other questions? We're just perfectly here at time. Please, if you're available, Saeed and Nicole and Maria, to continue monitoring the chat, that would be fantastic. I know people will think up questions as they get their coffee or go on